This video is about isomorphism, and we've got 4 objectives. We're going to define some terms, including injective, surjective, and bijective linear transformations. Then we're going to look at some examples where we decide if a linear transformation is injective or surjective. Then we're going to define invertible linear transformations and look at some examples to decide whether a linear transformation is invertible. We'll start by defining injective. A mapping T from U to V is injective if every element in V is the image of at most one element in U. We also call injective mappings one-to-one sometimes. We can picture an injective mapping like this. Here's the set U, here's the set V, which are going to be vector spaces in this course. Here's the mapping T, which will be a linear transformation, and each dot over here in U corresponds to a vector in U. Each dot here in V corresponds to a vector in V, and we can see that this vector in U is mapped to this vector in V, etc. And every element in V, so all of these, is the image of at most one. So at most one means one or none. 0 is included in at most one, so this one, and this one are images of nothing over here in U. In other words, they don't have any arrows coming in. And these 4 here are images of one element in U. If we had another element, say this one here in U, that was mapped over here to the same element here in V, this would no longer be injective, because now this element is the image of 2 elements in U, namely this one, and 2 does not satisfy at most 1. A mapping from U to V is surjective if every element in V is the image of at least one element in U. Surjective mappings are also sometimes called onto. Notice the difference in the definitions here. The only difference between the definition of injective and surjective is the single word most in the definition of injective is changed to the word least in the definition of surjective. So the definition of injective has this phrase at most one in it, and the definition of surjective changes that phrase to at least one. And we can picture a surjective mapping like this. Again, we have U and V. We've got elements in U that are mapped to elements in V. This time, every element in V is the image of at least one element in U. There are no elements here in V that are not images of an element in U. We can also see that some of the elements in V, like this one and this one, are images of more than one. But more than one is included in at least one. At least one means 1, 2, 3, 4, 5, etc., but not 0. At most one means 0 or 1, but not 2, 3, 4, 5, etc. If I had some elements like these green ones here inside V that were not the image of any vector in U, then T would not be surjective. Okay, now we come to our first theorem. A quick word about the theorems in this video. Since there's a lot of material to cover in this video, I'm not going to go through any of the proofs. Many of the theorems have proofs, some of them don't. All the proofs are in the book. I encourage you to read the proofs in the book as well as the proofs here in the notes. The proofs in the notes will be probably very similar to the ones in the book, but also probably not exactly the same, which is a good thing in as much as it gives you 2 versions of the proof. So if one of them is a little bit hard to understand, the other one might be more understandable, and the 2 of them together might be easier to follow. Okay, so the first theorem here says a linear transformation T from U to V is injective if and only if T of x equals T of y implies x equals y for every x and y in U. Actually, this theorem is not in the book. This is the definition of injective in the book, and the definition of surjective in the book is different than the one that I just gave as well. The reason that I use the definitions that I do is so that you can see how close injective and surjective are in terms of the wording of the definitions, and also how different they are in terms of what they mean. This is a great example of how changing literally one word in a definition completely changes the meaning. Okay, so let's understand what this theorem is saying. It's saying that if the image of 2 vectors is the same, if the image of x under T is equal to the image of y under T, that implies that x equals y. Intuitively, we can see why this theorem is true if we look at our diagram again. Here's a vector in V. If it is the image of x and the image of y, this single vector is both of these. It's t of x and it's t of y. Well, that means that this vector over here has to be both x and y. In other words, this vector is equal to x and it's equal to y. It's the same vector. That's different than a surjective transformation like down here. If we said that this vector is equal to t of x and t of y, well, here's x and here's y. And since they both get mapped over to this vector, it's possible for x to be a different vector than y, and this vector to be the image of both of them. So this transformation is surjective, but it's not injective because it doesn't satisfy the definition of injective. And in particular, if t of x equals t of y here, that doesn't necessarily mean that x has to be equal to y like it does over here. Okay, we're going to focus on injective transformations now for a while, and then we'll look at surjective transformations in the next section. The next theorem says that a linear transformation is injective if and only if the kernel of that transformation is equal to the set containing the zero vector. In other words, the kernel of T is the zero subspace or the zero vector space. This will be a really handy theorem to use when we're trying to decide if a given linear transformation is injective. We just find the kernel like we learned to do in a previous video, and if it's equal to the set containing the zero vector, T is injective, and if it's equal to anything else, T is not injective. The next two theorems are very similar. Theorem 1.3 here says that if I've got this transformation T from U to V, if it's an injective linear transformation, and this set S is a linearly independent subset of the domain U, then this set R, which is the set of the images of the vectors in S, is also a linearly independent subset of V. That's kind of a complicated statement, but you can think of this theorem as saying injective transformations preserve linear independence. And what we mean by that is if I have a linearly independent set in the domain, the images of the vectors in that set will also be a linearly independent set in the codomain. This next theorem expands on that idea. Again, if I've got a linear transformation T from U to V, and B is a basis for the domain U, then T is injective if and only if the set C containing the images of those basis vectors is a linearly independent subset of V. The last theorem here is also really useful when we are asked to decide if a given transformation is injective. If T is injective, then the dimension of the domain has to be less than or equal to the dimension of the codomain. We will often use the contrapositive of this statement. In other words, if the dimension of U is not less than or equal to the dimension of V, then T is not injective. Well, not less than or equal to means greater than. So here's the contrapositive of the theorem. If the dimension of U is greater than the dimension of V, then T is not injective. Be really careful. Injective and surjective are two totally different things. If T is not injective, that doesn't mean that T is surjective. Transformations can be injective and not surjective. They can be surjective and not injective. They can be neither injective nor surjective, and they can be injective and surjective. So injectivity and surjectivity, if you will, are completely separate things, and knowing whether a transformation is injective doesn't tell you anything about whether the transformation is also surjective, unless you have some extra information, and we'll see how that works towards the end of the video. Okay, let's do an example. Let's say we have this transformation T from P2 to C3, defined by T of P is equal to P of 0, and P of 2. We want to know if T is injective and why or why not. Well, in a previous example, we saw this linear transformation and we found the kernel. So if you go back and look at that video, you can see that we found the kernel of T. Here's the work again if you want to go through it, but we can skip to the end. And you can see here's the kernels, the span of the set containing this polynomial minus 2x plus x squared. Well, this is not the set containing the zero vector. The zero vector in P2 would be just the number 0. And the theorem that we saw earlier said that T is injective if and only if the kernel of T is equal to the set containing the zero vector. Well, since the kernel is not equal to that set, T is not injective. Simple as that. Here's an even easier example. In this case, T maps from P3 to C3, and T is defined by this function rule. T of this third degree polynomial is a minus d, b plus c, a plus b minus c. Again, we want to know if T is injective and why or why not. Well, the dimension of P3 is 4, the dimension of C3 is 3, and 4 is greater than 3. So by theorem 1.5, that says that the dimension of the domain has to be less than or equal to the dimension of the codomain. If T is injective, we can say that T is not injective because the dimension of the domain is bigger than the dimension of the codomain. In the last example here, we have another mapping from P2 to C3 given by this function rule. T of a plus bx plus cx squared is a plus b plus c, a plus c. We want to know if T is injective here. Well, we could try to apply theorem 1.5 again, but the dimension of P2 is 3, and the dimension of C3 is also 3, so that theorem doesn't tell us anything about T. If we go back and look at it really quick, notice it says if T is injective, then the dimension of the domain has to be less than or equal to the dimension of the codomain. But the converse is not necessarily true. This is not an if and only if statement. In other words, if this is true, well, T may or may not be injective. It could be, but that doesn't mean it has to be. So coming back to this example, because the dimension of P2 is the same as the dimension of C3, we need to do a little bit more work to answer this question. And in particular, we'll find the kernel of T like we did before. Remember, the kernel is the set of all the vectors P in P2 that satisfy this equation, T of P equals 0. They're all the second degree polynomials that get mapped over to the 0 vector in C3. So here's the 0 vector in C3. Okay, to solve this equation, we're going to replace the vector p with an arbitrary polynomial in P2, which we write using the function rule here, the definition of t, and set it equal to 0. Then what we have here is a vector equation. We use the definition of vector equality to write a system of equations. If these two vectors are equal, that means this component has to be equal to this component has to equal this one, and this one equals this one. We can write this system of equations like this, including an a, and b, and a c term in each of the equations. And now we've got a system of 3 equations and 3 variables, and we can solve by row reducing the coefficient matrix. Here's the coefficient matrix. It row reduces to the identity, which means a plus 0b plus 0c equals 0, b equals 0, and c equals 0. And the trivial solution is the only solution, so the kernel of T is the set containing the 0 vector, and by the theorem that we saw earlier, we know that T is injective. Okay, let's consider surjective transformations now. A linear transformation, T from U to V, is surjective if and only if, for every vector V in the codomain, there is a vector U in the domain so that T of U is equal to V. This is the definition of surjective in the book. I proved it as a theorem since I used a slightly different definition. A really handy theorem to help us decide if a transformation is surjective says that a transformation is surjective if and only if the range of the transformation is equal to the codomain. So when we want to decide if a transformation T is surjective, we find the range, and if it's equal to the codomain, then the transformation is surjective, and if it's not, the transformation is not surjective. That's because this is an if and only if statement. We can summarize 2 of the main theorems we've seen by these 2 points. If we want to decide if a transformation is injective, see if the kernel of T is equal to the set containing the 0 vector. To decide if it's surjective, see if the range is equal to V, the codomain. Then we have 2 theorems that are very similar to the theorems we saw about injective transformations. If T is surjective, and S is a set of vectors that spans U, then the images of those vectors, the set R containing those images, also spans the range. Down here, if T is a linear transformation and B is a basis for U, then T is surjective if and only if the set containing the image of those basis vectors is a spanning set for V. Similar to the theorems we saw about injective transformations, we can say that surjective transformations preserve spanning sets. So if I have a spanning set in the domain, the set containing the images of those vectors in the codomain will also be a spanning set. The last theorem in this section is similar to the last theorem in the previous section. If T is a surjective linear transformation, the dimension of the domain has to be greater than or equal to the dimension of the codomain. And again, the contrapositive of this theorem will be really useful. If the dimension of U is less than the dimension of V, then T is not surjective. Okay, let's look back at the same 3 transformations we looked at in the previous section and consider whether they are surjective and why or why not. So here's the first transformation we saw from P2 to C3 given by this function rule. And in order to answer this question, we have to find the range. Well, we also found the range in the previous video, so we can review the work here just for reference, but for now I'll just skip to the end. And we can see the range is equal to this set. And clearly this is a 2-dimensional subspace, and it's a subspace of C3. C3 is 3-dimensional, so the range is not equal to C3. Therefore, by theorem 2.2, T is not surjective. We saw earlier that this transformation was not injective because the dimension of P3 is 4, which is bigger than the dimension of C3, which is 3. But that's totally fine if we're trying to decide if T is surjective. This transformation might be surjective. In fact, the limitation on being surjective is that the dimension of the domain has to be at least as big as the dimension of the codomain, so being bigger is fine. Well, we'll find the range. As usual, we use the function rule, and we're going to factor this vector like this. So we can see that the image of any vector in P3, this vector in C3, which is the image of this vector in P3, can be written as a linear combination of these 4 vectors. And so the range is the span of the set containing these 4 vectors. Now we need to know if the span of this set is equal to C3. To do that, we see if an arbitrary vector in C3 can be written as a linear combination of these 4 vectors. So here's a linear combination of these 4 vectors. Here's an arbitrary vector in C3, x1, x2, x3. Well, if we had specific numbers for the values of x1, x2, and x3 here, we could just solve this system for a, b, c, and d. It's a little bit trickier since we don't. But regardless of what these numbers are, if we write down the augmented matrix and row reduce it, as long as there's not a pivot in the last column of the augmented matrix, we know the system is consistent, and therefore a solution exists. And that means that, yes, an arbitrary vector in C3 can be written as a linear combination of these vectors, and that means that the span of this set is indeed equal to C3. Well, if we just take the coefficient matrix of that system, which is here, and row reduce it, we can see that we get a pivot in every row of the coefficient matrix. So there's no pivot in the last column of the augmented matrix. Therefore, the system is consistent. The span of that set, which is the range, is equal to C3. And by the theorem we saw earlier, T is surjective. Okay, the last example here, T maps from P2 to C3. Here's the function rule. We want to know if T is surjective. Well, the domain of P2 is 3. The domain of C3 is 3. So it could be surjective. We don't know for sure. We have to check. We'll find the range the same way we did in the previous example. We take the function rule. We factor this vector, like so, into a linear combination of these 3 vectors. And so the range is simply the span of the set containing those 3 vectors. And now we want to decide if this set is equal to C3, we'll do the same thing. We'll put these 3 vectors into a matrix and row reduce. We do that here. It row reduces to the 3 by 3 identity, and we've got 3 pivots here. There's no pivot here in the last column of the augmented matrix then, and we know that the range is indeed equal to C3. Okay, now we come to the main topic of this video, which is isomorphism. We'll start with the definition of the identity transformation. So if a V is a vector space, the identity transformation on V is written with a capital I and a subscript V. So we don't use T, we use a special letter, capital I, and subscript V to indicate what the domain and the codomain are. Notice that this is a transformation from V to V. And the function rule is the identity transformation of V is just equal to V for all V and V. Well, that's a lot of V's to keep track of. A picture can clarify how simple this really is. I've got the set V here and here. It's both the domain and the codomain. I've got the same vector, little v, here and here. And the identity transformation simply maps V to itself. Now we can say that a linear transformation T from U to V is invertible if there exists a transformation S from V to U. Notice backwards from V to U, such that S circle T is equal to the identity transformation on U, and T circle S is equal to the identity transformation on V. We call S the inverse of T, and we write it like this. S is equal to T inverse, much like a matrix. We can picture that like this. Here's U, here's V, here's the little vector U in U, here's little v in V. T maps U over to V. S maps V back over to U. So the inverse S just undoes what T does. If T takes U over to V, S undoes what T does, and it takes V back to where it came from, back to U. Here's S circle T. It takes U and brings it back to itself. So S circle T of U is S of T of U by definition of a composite mapping. Well, T of U is just V. So the image of U under T, well, U goes over here to V. So V is equal to T of U. Well, what's S of V? S takes V back to U. S of V is U. So S circle T of U is U, and that is the identity transformation. Remember, the identity transformation on U takes any vector in U back to itself. Likewise, T circle S of V is V. It's the identity transformation on V. It takes any vector in V back to itself. So T circle S of V is T of S of V is U, T of U is V. We'll say that a mapping that is both injective and surjective is called bijective. Bi meaning two, and in particular it's both injective and surjective. And this theorem tells us why bijective transformations are important. A linear transformation T from U to V is invertible if and only if it is bijective. In other words, if and only if it is both surjective and injective. We will take this theorem to mean that bijective and invertible are essentially synonyms. So if I say that a transformation is bijective, that's the same as saying that it's invertible and vice versa. The next theorem here tells us that the inverse of a linear transformation is unique. This theorem is really important because if the inverse of a transformation were not unique, we wouldn't be able to talk about V inverse. Now we can define isomorphism, which is a fancy word. It just means an invertible linear transformation. We'll say that two vector spaces U and V are isomorphic if there is some linear transformation T that is invertible that maps from U to V. In other words, U and V are isomorphic if there's an isomorphism, namely T, between them. And we use this notation to say that U is isomorphic to V. You might remember this symbol from geometry or trigonometry. This symbol means congruent. So if you have congruent triangles, we'd use this equal sign with a little tilde above. Well, in linear algebra, this means isomorphic, and in particular, that means that there exists some isomorphism, an invertible linear transformation between U and V. The next theorem says that if U and V are isomorphic, then they have the same dimension. This theorem is sometimes called the round-trip rule in algebra or calculus. If you do T of T inverse of V, you just get V back. Likewise, if you do T inverse of T of U, you get U back. This theorem says that the inverse of the inverse is the original transformation. So if you take the inverse twice, you just get back to T. This one says that the inverse of a composition, if S and T are both invertible, the inverse of S circle T is the inverse of T composed with the inverse of S. In other words, it's T inverse circle S inverse. Notice the order changes. Inside here it's S circle T, and here T inverse comes first and then S inverse. In a previous video about matrices, we defined the rank of a matrix to be the dimension of the column space of the matrix. Now we're going to define the rank of a linear transformation to be the dimension of the range of the transformation. So we denote the rank of T by R with T in parentheses, and it's simply the dimension of the range of T. Likewise, the nullity of T is defined to be the dimension of the kernel. Remember, the nullity of a matrix is the dimension of the null space. The nullity of a transformation, written n of t, is the dimension of the kernel of the transformation. The next theorem tells us if we've got a linear transformation, it's surjective if and only if the rank of the transformation is equal to the dimension of the codomain. This is similar to a previous theorem, and in fact, that theorem is used in the proof here. The previous theorem says that T is surjective if and only if the range is equal to the codomain. Well, here we're saying the dimension of the range is equal to the dimension of the codomain. The next theorem says that if T is a linear transformation, then it is injective if and only if the nullity of T is equal to 0. And again, this is based on the previous theorem that says T is surjective if and only if the kernel of T is equal to the set containing the 0 vector. Well, the nullity is the dimension of the kernel, and the set containing the 0 vector has dimension 0. Finally, the last theorem in this section is the rank theorem for linear transformations, one of the most important theorems in this section and in the course, really. If T is a linear transformation from U to V, then the rank of T plus the nullity of T equals the dimension of U, the dimension of the domain. Remember, the rank theorem for an m by n matrix A says that the rank of A plus the nullity of A is equal to n, the number of columns in the matrix. This one says that the rank of the transformation T plus the nullity of the transformation is equal to the dimension of the domain. We'll see how this theorem will be a useful shortcut in some of the examples that follow. So let's look back again at the 3 linear transformations that we've looked at in the previous 2 sections, and now we want to see if these transformations are invertible and why or why not. Previously, when we did this example, we saw that it was not injective and it was not surjective. Well, in order to be invertible, it has to be both injective and surjective, and it's not either. So clearly, t is not invertible. For this transformation, defined by this function rule, we could go back and look and see whether this was both surjective and injective, but there's an even easier way to solve this. Notice that the dimension of P3 is 4 and the dimension of C3 is 3, and the dimension of the domain is not equal to the dimension of the codomain. Well, remember this theorem says if U and V are isomorphic, the dimension of the domain has to be equal to the dimension of the codomain. Well, what does isomorphic mean? It means that there is an invertible linear transformation from U to V. Well, another way to think of this theorem is it's saying if you start with a linear transformation and you want to know if it's invertible, the dimension of the domain and the codomain have to be equal. Why? Because if T is invertible, then it's an isomorphism, and therefore U and V are isomorphic. Well, if U and V are isomorphic, their dimensions have to be equal. So by theorem 3.3 that we just saw, since the dimensions of the domain and the codomain are not equal, T is not invertible. In this last example, we have a transformation T from P2 to C3. Well, the dimension of P2 is 3, the dimension of C3 is 3. So far so good. T could be invertible. We have to check to see if it's both injective and bijective. Previously, we saw that T was injective and surjective. Therefore, it's bijective, which means it's invertible. But what if we hadn't already done that work? What if we hadn't figured out that T was injective and surjective before? What if we were just starting with this example and we were given T and we wanted to know if it was invertible? Well, it turns out that we can find either the kernel or the range, but we don't have to find both. So we can use the rank theorem as a shortcut. Let's say we found the kernel. And as before, if we found the kernel, we'd find it to be the set containing only the zero vector. So that would tell us that T is injective. And one of the theorems we just looked at would tell us that the nullity of T is just the dimension of the kernel. The nullity of T would be 0, because remember the dimension of the zero vector space, the set containing the zero vector, is 0. Well, once I know the nullity, I know the dimension of P2 is 3, I know the nullity is 0, so the rank of T has to be 3. Well, remember theorem 3.7 here says T is surjective if and only if the rank of T is equal to the dimension of V, the codomain. And in this case, the codomain is C3, so its dimension is 3. And since the rank of T is also 3, we know that T is surjective. We know T is injective. Theorem 3.7 tells us that T is surjective. Therefore, it's invertible. Similarly, we could have found the range first. We would have found it to be the same thing we got before. The range would have been the span of this set, and we could see, oh, the dimension of the range is 3. As before, since the rank of T is equal to 3, which is the dimension of the codomain, by theorem 3.7, we know T is surjective. The rank theorem tells us that the nullity of T has to be 0. And then theorem 3.8 says that because n of T is equal to 0, T is injective. Well, it's surjective and injective, therefore it's invertible. All right, that finishes this video on isomorphism. We defined injective, surjective, bijective, and invertible transformations, and we did a bunch of examples to decide if a transformation is injective or surjective and therefore invertible.